right, so we're at session 2 now. Hopefully you've already submitted your assignment for session 2 before you watch this video. That must be done before you view the solutions. Okie dokie, just like last time, if you feel like you need to stop the video while you edit, feel free to do that. So number 1, if you click this link, it's going to take us to a website where we're going to use this to help us describe differences and similarities between a number, a numeral, and the name for a number. Okay, so if you click the link, it should take you here. This is not the only place you can find this information. It's just the quickest and the easiest that I found. So a number is a count or a measurement, and it's kind of an idea in our minds. Okay, so when we write or talk about numbers, we are usually using numerals. We're talking about 4. Okay, so using that order, okay, that count, that numeral, we're talking about 4, the actual number or 4 in words. But that's not the only way to show that worth. We could also hold up 4 fingers. We could tap the ground. There's lots of different ways to represent the number. Okay. In terms of using the numerals, okay, here we're talking about the actual item itself, okay, the entire number that we see or what we would write down, okay. A numeral is a symbol or a name that stands for a number, okay. So 3, 49, 12, any way that we give it an official name, then that's what we're talking about as the numeral. When we get to basically breaking this down, I like this sentence especially well for this. The number is an idea. It's kind of like a concept in our head. The numeral is how we write it. We can use the words, we can use the symbol, okay? However, when we're making these symbols, a single symbol is a digit, okay? So let's think about this. The numeral 153 is made up of 3 digits, 1, 5, and 3. Okay, the numeral 46 is made up of 2 digits. So it's very important when we talk about number concepts, especially to young kids, that we're conscious of how we use this. I'm not saying that your kindergartners are going to be up for a discussion about the difference in number, numeral, and digit. But as they get older, this is something that we want to be more aware of and make sure that we show them that and we talk to them about the difference. Okay, so when we say the number, if I were to say 10, okay, in your head, you have a vision of 10 of something, of what it's worth. Okay, that's an idea. If you were going to write that idea down, you would use a numeral. You would write the word 10, or you would write 1, 0, using the digits 1 and 0. Okay, so I hope that makes that a little clearer. Okay. What's the difference between an ordinal and a cardinal number? You could have Googled that. Perfectly fine with that if you did. However, if you remember from your syllabus, we do have mathwords.com, which is a fairly decent little math dictionary for basic concepts. Cardinal numbers, 1, 2, 3, 4, okay, as we're going to call that number out loud. Ordinal numbers, though, if you click on that, it's going to tell you these are indicative of order. So first, second, third, fourth, and so forth. That's the difference there. Now, we have been discussing in class sets of numbers when we're dealing with our numbers that we work with frequently. We are going to use those sets that we've talked about. Remember, we discussed from natural as being the most specific. Then we move up to whole, which adds the 0. Then we move up to integers, which adds the negatives. Then we move up to rationals, which add the fractions that terminate or repeat. We also have a set of irrational numbers, which do not terminate and do not repeat. And together, irrational and rational numbers make up all real numbers. So based on that, we're going to go through these values and indicate which sets they fit in. Okay. Number 3 is a negative fraction. You could simplify it to 1/6 if you wanted. It doesn't change anything. It is going to be a rational number and a real number. Square root of 2, if you were to perform that on a calculator, Okay, it's not a perfect square root. You should know that. Since it isn't, okay, that means it's going to be irrational. If it's irrational, it can only be irrational and real. 10.125, that is a terminating decimal. It ends. Okay, so that is a rational number. If it's rational, it must also be real. Pi, as shown here, this is a never-ending, never-repeating decimal, so that's irrational. If it's irrational, it's also real. Number 3, 0.01, we know that's the same as negative 1/100th. So since that's represented decimal / fraction, then we are dealing with a rational number and a real number. -4, of course, would be an integer. It is a opposite of a whole number. Okay, so it's an integer. If it's an integer, it must also be rational. It must also be real. 0.6, that little sign indicates that's repeating. Okay, since it repeats, it fits in the rational category. If it's rational, it is also real. Okay, now for these last two, you might be tricked. You might look at the first one and you think, oh, it's a fraction, it has to be rational and real. But we always want to think about our fractions in simplest terms. Okay, so if we have 20/5, that actually simplifies to 4. It's just another way of showing it. So even though it looks like a fraction, it's worth 4. So that must be a natural number, a whole number, okay? An integer, a rational, and a real number. Start on the inside and work our way out. And square root of 225, if you actually take that, that is a perfect square. It is 15, okay? Again, same scenario as the previous example. We are dealing with a natural, a whole, an integer, rational, and real value there. Okay, so number 4 asks us, does the Roman numbering system use place value and back up your answer with evidence? Not in the traditional sense. Okay, what do I mean by that? As they move left or right, placing a significant letter somewhere, it's not in the traditional sense that we would think of as place value. However, position in their number system does have some meaning. Okay, now what does that mean? Think about the difference in the way you would place IV and VI. Okay, IV would mean 4, VI would mean 6. So not in the traditional sense, but yes, position does matter here. In the Babylonian system, what problems might happen if you don't use the colon to separate place values? You're going to lose track of what it is that you're counting exactly. Okay, we no longer know if we're representing ones, if we're representing 60s, if we're representing 3600s. You know, we have no idea here. Okay, so we wouldn't be aware of what place value we were representing. For us in our number system, I mean, position matters to us. We don't separate with a colon. We do use commas, but it doesn't have the same purpose. It would be like, instead of me writing my numbers in a line and working left to right, I just wrote them randomly across the board. In different spots. You wouldn't know how they went together. You wouldn't know what place value that's representing. Jack discovered in climbing the beanstalk that the giant had a numeration system based on fee, fi, fo, fum. When the giant counted his golden eggs, Jack heard him count. Fee, fi, fo, fum. Fought, fee fought, fi fought, fo fought, fum fought, fee fought. Jack believes that the giant has 20 eggs total and wants to know what other numerals, so remember we're naming these values, might be used to finish counting to 20. Okay, so it's really important that you see what we have here and try to make sense of it. All right, whenever I'm stuck with a problem where I'm totally confused, and if hearing a giant count in fee, fi, fo, fum does not confuse you, nothing will, right? So I try to make sense of what I'm looking at in front of me. I'm going to assume that fee, fi, fo, fum is the beginning of his counting. So I'm going to assume fee represents 1 egg, fi 2, fo 3, fum 4, and obviously fought 5. Okay, if that's the case, I've established words or numerals for quantities up to 5. 1 fee, 2 fi, 3 fo, 4 thumb, and 5 thought. Okay, if that's the case, now we start to see combinations of those. Just like in our numbering system and in other numbering systems, start to see combinations, that usually means there should be something logical about how these are put together. So we believe that after thought, the next value should be 6. And the numeral or the name we've been given, if what we think holds true, is phi thought. Okay, so let's look back at what we've established already and see what phi thought would represent. Phi would represent 1, thought would represent 5. So 1 and 5 is actually 6. So that reassures me that my reasoning is pretty good. If I move up to 7, okay, I see phi thought. Phi is 2, thought is 5. That makes sense. Faux thought, 8, 3, and 5. Thumb thought, 4 and 5. Thought, 5 and 5. Okay, now we've got a combination of 3. So we've shown 10 up to thought. And now we're at phi thought. Okay, if we go by what we've already established to make sense, that would be 1, 5, and 5, which is significant with 11. Okay, so phi thought. Phi thought, faux thought, thumb thought would get us up to 15. Okay, after we've got up to 15, we might start over again. Okay, phi thought. Phi thought. Faux thought. Thumb thought. Thought. Okay, once we get up to 20. So again, I know that's confusing and it seems like the craziest thing ever. Kids would love it. And it really brings back that idea of the naming of a numeral having significance in terms of value. Okay, so number 8 is a Mayan counting system. Okay, and it's a pretty advanced system. Some examples of Mayan numerals are shown below. It's important to know that the line represents 5. We have a dot for a 1, and we have like this little leaf-looking symbol for a 0. Okay, so numbers are stacked vertically instead of written horizontally. And traditionally, if we're representing a number of 5s, a number of 1s, or a number of 20s, we're always going to put dots on top of the lines. Okay, the top group of symbol is 20s, and the bottom group is 1s. So the taller the grouping, the higher its place value. Okay, so the first question wants to know is, explain why the first and last examples represent different numbers. Okay, so if you look at the first example and the last example, they look like they have the same elements. Okay, however, if we look at the explanation underneath them, the very first example over here on the left, okay, it follows the rules up here for dots above the lines. Since that's the case, we're going to assume that these belong to the same grouping. There's no other grouping on top of them, so they have to be counting 1s. And that would be 5 plus 2, which would be 7 1s. Okay. Now over here, we see, even though we have the same items, we're not following the rules here. The 1s are not above the lines. And what that tells me is we've transitioned into another group here. Those 2 belong to the 1s, whereas up here we've started another group of 20s. So we have 5 20s plus 2 1s, which is 102. Okay. When we start to see divisions, that can be an issue. Now, the next question is, well, how would you know to separate groups if you had similar counts? Well, they do have a symbol for 0. Okay, so that would help. All right, next question wants us to write 56 and 289 using Mayan symbols. Okay, so I'm going to try to pull up my active pen here and see if I can draw this without making a mess of it. So we've got 56, and we can use 0s, 5s, and 20. No, wait a minute. We can use symbols would be our lines for our 5s and dots for our 1s. Okay, that we have to group this in 20s. Okay, we can count 1s and we can count 20s. How we count them would be using these symbols. Okay, so I'm going to kind of think about this at first. Got my 56. Now I have to break up 56 into 20s and 1s. Okay, so we always want to break up with the largest we can first. So I need 2 20s. And then I'm going to need 16 1s. Okay, so how can we show that? First, let's show our 20s. Okay, there's my 20s. Now I'm going to show my 16 1s. 15 and then 16. Okay, I had a lot of students say, well, how do I know that these 3 dots don't go together? Remember, they are layered vertically here. So if these were all counting 1s, those 2 wouldn't be up there by their lonesome. They'd be down here with it. If this one was counting 20s, it would be up here in a line with these. Okay, and we might have to separate them. Somehow we might have to have 0 going on there. Okay, so all right, moving along. Let's go to 289. Okay, when I look at 289 here, I'm going to need 14 20s. Okay, that's going to give me 280. And then I'm going to need 9 1s for the remainder there. Okay, so I'm going to show my 20s first. I need 14 of those. So 1, 2, 2, 3, 4. So there's my 14 20s. And now I need 9 1s. So a 5 and 1, 2, 3, 4. So 9 1s. So here's my 9 1s. Here's my 14 20s, which gives me 289. Okay. It asks us now to explain how we know that the Mayans did not use a base 5. Whenever we're trying to write our digits in our numbering system, we group by tens. Okay, so to transition out of the ones place, we have to have 10 of something to move up. Here, if you look at the structure of the Mayan system, once we transition out of the ones place, we're not moving into how many 5s, we're moving into 20s. This is a base 20 system, okay? When we count our values, okay, when we're showing the characters for that, we're representing 1s, and then we are transitioning up to another grouping, which is 20s. We may have a symbol that's worth 5, but in terms of how we group and how we count the numbers, that's based on 1s and moving into 20s, which is what that base would be here. It says, we say our numeration system is anchored to 10s. What do you think that means? Okay, every time we get 10 of any particular place value, we trade up, okay? Or if we are trying to move down to smaller place values, we trade down. Either way, there's an exchange factor of 10 there. That is essentially what being anchored to 10 means. As we move through our place value, we are increasing and decreasing in powers of 10. Right? Chinese numbers are easier for children to learn because the name for the number is close to the math involved to create it. It's kind of like the giant's counting system in his example. For example, the Chinese word for 21 is precisely 2 10s and 1. What words for numbers are particularly hard for English-speaking children to associate with what they mean in value? Again, this is one of those questions where it could have had a lot of different answers. One of the ones that sticks out to me is 11 and 12. At least with 13, 14, 15, 16, and so on, we kind of get a clue about the word 3 or 4 or 5. 11 and 12 don't necessarily show that. 20 is maybe another one of those words that I might think they would struggle to learn that's not in this capacity. Okay, so now are our kids who've learned English their whole life and counted forever going to have trouble with that? No. But perhaps if they are ESL students who are used to their numbering system making sense like that, then that's probably something that you're going to have to think about. Okay. Now, if I move back up here, I think I might have skipped writing some numbers. Okay, I did. I skipped number 5. So I'm going to come back to number 5 and give myself some space here to be able to create these values. So we have 479 and 3657, and we want to write each one of these in 3 different numbering systems. Okay. So what I'm going to do here is I'm going to try to label E for Egyptian, B for Babylonian, and R for Roman. And I'm going to kind of draw a cross here. And I'm going to split this down the middle. Okay? I'm going to use this side for 479. And I'm going to use this side for 3657. Okay, so to start with Egyptian first, the Egyptian symbols, hopefully that we're going to see these in class. We're going to talk about them. Okay, Egyptian symbols are pretty much a base 10 system. They use different symbols instead of like our system where we use the same digits to count over and over again, but we're looking at pretty much a base 10 system. So for 429, the largest place value I have is 100. So I've got to represent 4 hundreds. Okay. 70, so I've got to represent 7 tens. And then I've got to represent 9 ones. Now, it doesn't have to be in order. Unlike our system, position is not important because the symbol itself guarantees worth. These are unique symbols among the digits, okay? So that's kind of different from our system. So if we go over to 3,657, we can do that as well. We need 3 of the 1,000 symbols. So this kind of looks like a little flower with a crescent moon on it. So that's 1,000. 2,000, 3,000. So there's my 3,000. And then I have 600. 1, 2, 3, 4, 5, 6. And then I have 50 and 7. Okay. So Babylonian, if we move into Babylonian, those use kind of like little, they almost look like inequality symbols and T-shapes, where place value is separated by colon. Okay, Babylonian system, like we said in class, is also based in 60. Okay, so what does that mean? We count ones until we reach 59, and then when we move up to the 60th, then we're going to roll over and start counting in a new place value. It's very similar to the situation in the system that we have here. Okay, so let's start first with 479. Okay, now we obviously know that we have some 60s in there. So it might be helpful, if you didn't already, to divide 479 by 60 to see how many whole 60s you're going to get there. Okay, so you should get 7. So I'm going to show 7. So that's 7 60s. Which, if you do the math on that, that should be 420. That's the worth of those 7 60s that we're showing. Then we're going to put ourselves a little colon here so we can transition to ones, right? And now we're going to count the ones that are left. So like I said, we have already counted 7 60s. That's taken up 420. So now I need to show 59 ones. So 5 of the little symbols for 10. And then I'm going to use 9 little T-shapes to represent 59. Okay, here we go. We're moving into a bigger number. But here's the thing. When we're counting in 60s, once we get to 60 squared, which is 3,600, we've moved into a new place value. Okay, so I have 1 3,600. So I'm going to use that symbol for 1. That's going to give me 1 times 3,600. Now, the only thing that's left after we show the 3,600 is 57. There are no 60s, okay? So those are 57 ones. We don't have enough to make a 60. So I've seen this shown a couple of ways. Okay, we might have something that looks like this. Where we have 2 colons. This is to let the reader know that's a 3,600. There are no 60s present. That's why we see nothing in the middle here. And then we have 57 ones. Okay, this is our 57 ones. Okay, I've also seen some people put a 0 in there. Babylonians did eventually develop a character for 0, but it probably wasn't yet in their development when they first started working with this type of numbering system. All right, last but not least, we got Roman numerals. So if you don't have the worth of those, you might have to look them up. So we're looking at 479. I'm going to show 400. I'm going to use the largest values I can. So there's 4 100s, which C is 4, represents 100. And then I need to represent 70 with the largest numbers I can. So L for 50, 60, 70. Okay. And then I've got to show 9. So IX, that would be 1 before 10. Notice that we're able to read this very well until we get here. This is the only place where we see a symbol with lower value in front of one with bigger. So that indicates a subtraction there. Okay. 400, 70, this is the 9. Okay, so let's come over to 3,600. We've got 3,000s to represent, so we do that with M's. So that's our 3,000. Okay, we need 600. So we have 500, 600. And then we need to show 57. So 57. Okay, here's my 3,000. Okay. This is going to be 600. There's my 57. Okay, I could have separated 50, which is the 1 digit to vote L there. All right, so hopefully it's been an interesting trip through number systems, seeing that our way of writing numbers is not the only way to do it on the planet, and also thinking about what makes our numbering system so unique. So once you've made your edits, you can go on to the reflection questions.